And finally, we achieved actually this state space model, which was represented, if we want to represent this in using the matrix formula, then this would become like this: x dot equals ax plus bu. So what we would like today, we would like to form this linearized representation. We would like to form in MATLAB, code it, and then we would also like to see the responses that would come from the analysis of this A matrix. Of course, with the application of some disturbance here in the U matrix. Okay. So specifically U here, for our case in equation number 22, this is a disturbance vector. So either we can apply the disturbance in the mechanical input side, or we can also apply some disturbance and observe the system dynamic response by applying, let's say, some step response, step disturbance in the exciter circuit. Okay, so let's jump into the MATLAB now. If you remember, we already had developed the initial condition file for an example SMIB system. So we would be continuing with that. So the linearized model that we will be developing actually would require the coding of these few constants here, okay? K1, K2, K4, and K3. So these 4K constants are the required parameters or constants that are to be calculated if we want to actually analyze this matrix. Another name for this A matrix, sometimes you would also find in the literature, it is also mentioned as the system matrix, because it gives you the idea about the dynamics of the system, okay, or the stability of the system based on some disturbance response. Other than these 4 constants, if we further look into the A matrix, then the remaining parameters are actually constants. So we have H, omega base, and TDO prime. Omega base is 2 pi f. H is the inertia constant, per unit inertia constant. D is the damping constant or damping coefficient, and should be given. And TDO dash, again, it's the dx is transient open circuit time constant. So we don't have to bother about those because we already have those values listed in our code. So we would be looking to form this, the expressions for K1 up to K4. And if we go back and look into the detail of this K1, K2, and K3, and K4, then we find that they are again some function of some other constants like C1, C2, P1, P2, and so on. So we would start from the beginning of the linearization process. So if we start from building C1 and C2, then we'll go slowly towards the K constants. So that would be the plan. So let's start then. Raise these things. So we simply copy the initialization file and make a new file. And that means we already have the initial conditions for the system calculated. So with these values, let's start with the formulation of the C1, C2. Okay, so as we go, we will continue with the variable names of the constant names. So what would be C1 here? And what would be C2 here? So C1 is the coefficient which is associated with del delta. So that would be VB. So because we used absolute of VB, probably check back, the absolute of VB is the absolute value. Sine of delta, delta 0. Yeah. Do you see the MATLAB window now? Do you see the
Yes.
mat?
Yes, sir.
Okay. So absolute of VB sine delta naught. So because delta was the initial condition we calculated. So this was the delta calculated at line number 18. So we'd be using that. So we are calling it simple delta. So VB sine delta naught divided by XD dash, that is XD prime, small letter, plus XD. So that is C1. C2 is simply 1 upon XD prime plus XD. So in this way, we would continue. Okay. So what is then C3? So this C1 and C2 are associated with delta ID. Then C3. So we continue with the formulation of C3. C3 would be simply VB cosine delta divided by XQ plus XT. So we can simply copy it from here. So that is VB cosine delta XQ plus XT. XQ was in a small font, so XQ plus XT is fine. So that is about C1, C2, and C3. Next, we formulate P1. Based on these C1, C2, and C3, we can now formulate some other constant coefficients that are required for calculating ultimately the K constants. So these are probably P1, P2, and P3. So this is P1, P2, P3. And from the derivation, we can take note of the expressions. So P1 is XQC3. XQC3. P2 was found as minus XD prime into C1. P3 is found as 1 minus XD prime C2. So this is about P1, P2, and P3. So that is done. Then we can go on and formulate our K3 parameter. So now formulate K3. K4. So K3 is again from the derivation that we got in the last class, XD minus XD dash into C2. That is K3. K4 is XD minus XD dash into C1. Okay. Now about K1 and K2. So if we go for K1 and K2, K1 would be VD. If we use VD, yes, VD and VQ. So VD C1 plus ID P1 plus VQ C3 plus IQ P2. So that is K1, and then we have K2 VD into C2 plus IQ into P3. So that is K1 and K2, K3 and K4. And probably we are almost done. So then we have to build the A matrix. Probably we are done. So did we define omega base? Yeah, omega base was defined in line number 10, that is 2 pi f. So let's formulate the A matrix now. This is the first row. Then this is this first element in the second row. Third element in the second row. Sorry, second element in the second row and third element in the second row. And we have the last row is this one, and this should be K4, 0 and minus K3 over GD over. So that is the 3 by 3 matrix, and then we should be able to calculate the eigenvalues. So let's save it somewhere. This is the eigen of SMIB. Let's make it third order. Okay, just save it. And if all our definitions and expressions are correct, we should get the eigenvalues listed below should appear here. Okay, so we have got 3 eigenvalues because the system order is 3. Now, what should be the conclusion regarding the stability for this set of eigenvalues for this SMIB system? So if I want to plot it in the S-plane, so simply I can write all this set of eigenvalue in general as sigma plus minus j omega. Okay, where sigma lies along the real axis and of course omega lies along the imaginary axis. So by looking at the set of these eigenvalues, we can see clearly that the first two, they comprise of a complex conjugate set of solution, and the third one is a real pole. It's not imaginary, with a negative real part. So let's say the third one is plotted somewhere here. And the first two, because they're complex conjugate, they have negative real part. So that would be minus sigma plus minus j omega. So that would be the complex pole. So these are the 3 poles. Now what about the stability? This is our 0, 0 point. So because all the poles are lying on the left half of the S-plane, this is our S-plane. So we can easily conclude that the third order system at this operating point, is small signal stable. So this is the conclusion. That means if you apply a small disturbance to this linearized system, you should get a stable response. The response would of course have certain characteristics. This is a stable system because of this group of eigenvalues. All of them have negative real part as seen from here. So what is the dominant, or what are the dominant eigenvalues here? Among these 3, which should be the dominant eigenvalues? Remember, the eigenvalues are nothing but the poles of the characteristic equation for this system. That means if you try to get the transfer function model, then of course you will get a relationship between the input and output of the system in S domain. And then you will get some characteristic equation in terms of S cube, because it is a third order system. And if you solve them, of course your solution would be something like S1, S2 and S3. So these 3 are nothing but the poles of the system. We can also say that these one are P1, the poles, P2 and P3, which are the poles of the dynamic system. So if all the poles lie on the left half of the S-plane, that is stable. Now, what is the frequency of this system or of this oscillation that would generate because of the dynamics of the system? To calculate the frequency in F, in hertz, what you have to do, simply you take the omega values. So these are the omega set of values. So you calculate F simply using this formula, omega over twice pi. And of course, in case of omega, because we see that there could be some minus omega part, okay, minus j omega. So simply you can take, instead of this, you can also write that this is like this. You take the real part, sorry, the absolute value of the imaginary part of the eigenvalues. Okay, so that would give you a positive value here, some positive value over here of omega, and then you divide it by twice pi. So that would be your f. So let's calculate this now in MATLAB. So our frequency would be absolute of imaginary part of our eigenvalues divided by twice pi. It is a vector, so you have to go for element by element operation. So dot division divided by twice pi. And now if you run it, you can also see the frequency of the system at which the oscillation will occur. Okay, so that means probably we have to give it some name. So let's say it is something like dd. So imaginary of dd. Or we can also say this is eigen of A. So there is a mistake. It should be eigen of A, or you may give it a variable name. Okay. So you see that the first one, second one has a certain frequency, and the third one has a zero frequency, because of course we can see from the eigenvalue dd that the third one doesn't actually have any imaginary part. That means the omega part is zero for the third one here. Whereas the first one and second one, they have a certain omega associated. And the corresponding frequency in hertz, it is only around 1 hertz, right? So what is the operating power frequency? The operating power frequency that we took for our example was written or listed in line number 6. That was 50 hertz. That is the power line frequency. But the frequency of interest for this calculation, for this SMIB system, is very, very less compared to the original power line frequency. So because of this range of frequency that the system will try to oscillate, or the system dynamics will oscillate, this kind of problem of stability, that is known as low frequency oscillation problem. Low frequency oscillation problem that you will find in the literature. Why it's low? Because you can see the magnitude of the order of the frequency, magnitude of order of the frequency, it's pretty less compared to the power line frequency. And in short, this sort of problem, in short, it is known as LFO, low frequency oscillation. Unfortunately for our case, in this case, we have a stable system, okay? But how much stable it is, okay? What is the stability? Is it acceptable? Well, if we are only interested in the question that whether the system is stable or not, if that is only our question or that is only our query, then fine, we are in the fine zone, we are in the safe zone. But there is another measure for this to identify actually how much safe you are in the stable zone, or how much damping, we call it in technical term, we call it how much damping is associated with this oscillation. So let's try to calculate that, and that is known as damping ratio. I hope you have heard this before. Can you define what is damping ratio? Or can you recall what is damping ratio for any dynamic system? Okay, no one is trying, so let's continue. So the damping ratio is simply, you can call it by zeta it is minus the real part of the eigenvalue of A So what is the real part of eigenvalue of A? The real part of eigenvalue of A is actually plotted here along the x-axis. So we can simply write this minus real of eigenvalue simply as sigma. Okay. So this numerator would be simply sigma and divided by. So I'm not going to write the detail again because I don't have that much space here. I'm simply writing it in terms of the symbolic representation. So sigma squared plus omega squared. So omega is again the imaginary part of eigenvalue of A, like this. So what that would give us is the idea about how much damping is associated with each of these eigenvalues. Okay, how much damping is associated with each of the eigenvalues present here in the system. So first, what we did, we simply calculated the frequency range of our interest. So the frequency range of our interest is very low. It's around 1 hertz for this example. It may go up to 2 hertz, okay, not beyond that. So 0.1 to 2 hertz maybe you can treat the problem as the low frequency oscillation problem. Okay, so now let's try to calculate this damping ratio zeta in MATLAB. So try to put it, zeta is MIB equals minus real part of eigen of A dot divided by square root real part of eigen A squared plus imaginary part of eigen of square. Hopefully it's correct. Otherwise, there will be some error. Okay, some syntax error would be given by MATLAB. So don't have to worry, just run it. Yeah, there is some issue. Okay, probably it should be elemental operation. Yeah. So you see, the amount of damping that is associated with the eigenvalues of the system, although it's a stable system, but the amount of damping that we are getting is pretty small. It's almost negligible. It's 0.0009. So in general, in conclusion, or as a thumb rule, we can set, or it is set actually, that if your zeta is less than actually 0.1, then it is a very lowly damped system. Okay, we call it low damped. And you need to adopt some measure to actually enhance the damping. Okay. So if zeta in general is less than 0.1, then although it might be stable, okay, we can see that, well, from the eigenvalue information, we can see that, well, it's a stable system. It has a negative real part, that's fine. Frequency is there in the low frequency zone, that's fine. The third eigenvalue is also stable, that is also fine. But the dominant eigenvalues, we are interested in the dominant eigenvalues actually. By dominant eigenvalue, we mean the eigenvalues which are closer to the y-axis, okay, real y-axis. So that would actually govern the dynamics of the system compared to this one, okay, which is far from the y-axis. So this set over here, which are closer to the y-axis, are the dominant poles or dominant eigenvalues. These are the dominant eigenvalues. And unfortunately, although the system is stable, the damping that is associated with this set of eigenvalues, the dominant set of eigenvalues, is pretty less than our set mark or the benchmark, that is 0.1. So that's why we should take some measure ultimately. Although the system is stable, we should take some measure to enhance this value of damping. That is, we got it actually 0.0009, very less. So we have to take some measure ultimately to take care of this low damping of the system and have some better damping out of the for the SMIB system. Any question up to now? Because we'll be moving into a little different, not different actually, we're moving into a different file for coding. Or even we can do it here, but we will do it separately just to make things separately understandable. Any question? No question. So let's proceed on. So with this, now we have got some idea about the damping ratio, about the frequency of the system, about the low frequency oscillation problem, and whether the system is stable or not. We can simply check the eigenvalues of the system matrix A. Okay, now the question is, actually we started from some nonlinear SMIB simulation. If you remember, this was the original file, or this was the coding done for the original nonlinear problem of the form x dot equals f of x comma u. Okay, so this was the original problem statement for the SMIB system, the nonlinear one. We got the response for that system. Actually, we coded it, and we actually applied some disturbance in the line number 43, if you remember, that is in the mechanical input power. So the disturbance was applied at 0.1 second. So before 0.1 second, the system was at steady state. And at 0.1 second, we actually applied a step type input, a step type disturbance that was of magnitude 0.2. And that was applied in the line number 43, that is in the state equation for omega. And we got some response. Now the question is that whatever system we have derived out of this system, out of this nonlinear system, we are claiming that we have got another system which is valid only around a certain operating point, and that can be represented by the linearized version of this block over here, and that is this one. And we have seen that, well, we can analyze the eigenvalues of A, we can get the frequency information, we can get the damping ratio information out of this, we can get the dominant eigenvalue information out of these things. But the main thing that is not answered yet is the linearization that that we have done actually around a certain operating point. The next question comes that whether this linear model provides the similar or identical kind of response to this nonlinear model or not. So that is one way actually to check back whether your linearization is actually correct or not, whether your linearized model is correct or not. So to check that, actually, we again have to do some simulation for this block over here, the time domain simulation that we did for this model in this file. So similar kind of simulation we will do. That means some numerical integration technique has to be applied for this linear model now. And then what we will do, we will apply the same disturbance that we had here. Same disturbance block would be applied here at the same point. That means at 0.1 second, we'll be applying disturbance of 0.2 magnitude per unit, of course. And we'll be applying the disturbance again in the mechanical input torque. And we will try to compare the responses that we got from the nonlinear system and that we will get from the linear system. And if the responses are almost identical, then we'll say, well, our linearization is good enough to proceed on with the controller design. Okay, so that is the next target. Okay, before we go there, let me talk a little bit about the coding that we did already. So another question that remains, we'll answer it probably in some later classes. Once we are done probably with some few more modeling, then we'll be answering this specific question that I'm going to place right now. The question is, we know that we have three states, right? For our this AX plus BU. This is the third order model. Third order model. So what are the states? States, if we list them, the states are delta, omega, and EQ dash. Okay. Fine. The question that is not answered yet is we actually do not know still that which of this eigenvalue or this complex pair of eigenvalue actually, or the third one actually, which one belongs to which state, or which one is coupled to which state. Okay, just by looking at these values over here, this block over here, it's not possible to answer this question. That means we don't know whether the first one is associated with delta, or the second one is associated with delta, or the third one is associated with delta or not. So that is the question that remains unanswered. Okay. Similarly, we don't know omega is linked with which one of these, and what is the amount of linking. EQ dash is linked with which one of these three, and what is the amount of linking. Okay. This is known as the participation. Okay. This is known as participation. So that means this participation, and specifically the participation factor. The participation factor knowledge or information of the participation factor, calculation of the participation factor will actually give us the idea about which of these state is actually linked with which of these eigenvalues. So that would give us the amount of participation made by each of the states in each of the eigenvalues. So that is actually the definition of participation factor. Why is it important? Well, for this case, we can say the system is stable. Even then, if we can know this participation factor, then we can probably design a controller by tracking those specific states, or by recording the information of those specific states and trying to design the controller to control those states only. The minus 0.2373, that is far away from our y-axis, that is in the negative half of the S-plane. So we don't have to bother for the time being about the third one over here, third state, or the third eigenvalue actually, to be specific. The first two are of concern, of major concern, because they have very low damping. Their damping amount is 0.0009, 0009. So it's very lowly damped. So if we can identify the specific states which are associated with these two, then it would be easier for us to record, or to, let's say, if I want to design simply feedback controller, PID controller, or PI controller, or any optimal controller, or any kind of controller, then of course we have to record those actual values of those specific states which are associated with these two lowly damped states, or lowly damped eigenvalues. And due to that, we need to know actually this information, the participation factor. So in some later classes, probably I will show you how to calculate this participation factor, so that before designing any controller, we can have the idea about which state are to be tracked, which state are to be observed, and which state are to be controlled ultimately. Okay. So that is the essence of participation factor calculation. Any question? No question. Okay. So now let's try and simulate this linearized model and try to obtain some responses out of it. Okay, so what we have to do, we have to, what is the linearized model? Yeah, this is the linearized model. So you can copy this and paste it here. And all the things that are listed there are required for us. So we simply keep them, but we want to actually simulate the equations, which are this. So let me write down the equation at the top somewhere here. Okay. So let me use the text block now. So we have del delta dot. So what was del delta dot? It was omega 0 or omega base into del omega. So that was the first equation. So I'm simply listing the state equations in the x dot equals ax plus bu form, okay, because I would like to quote them. So del omega dot, it was minus, okay, I can put 1 upon 2h now, 1 upon twice h multiplied one bracket, some third bracket, minus k1 capital del delta minus d into del omega space it's pretty small. Is it visible, the font, the blue one?
Yes, sir.
Okay. So we have minus k1 del delta minus d del omega, and then minus k2 del eq prime. K2 del eq prime. And actually we also have some plus del pm. That is our disturbance in this state. So that is our second state equation. The third state equation is minus, del eq prime dot equals 1 upon t do prime multiplied by minus k4 del delta minus k3 del eq prime plus del eft. I think it is okay. Okay, then first we code it and then we can check back again, no problem. So now let's code it. So first, what we have to do, we have to again define some parameters associated required for the coding part. So because we'll be going for the Euler method of numerical integration. So where is that file? This one is not this one. Yeah, the nonlinear simulation part is required. So let's take this block and we can update that as per our requirement. Semi-B was that untitled one. Okay. So again, we are defining our simulation time. So we are taking the 30 seconds as the total simulation time. TS is the sampling time. T, we are defining or initializing the time vector all to zeros. And the size of that vector should be, of course, equal to the total number of steps that we are going to simulate. And that is TC divided by TS. And disturbance time, we are going to apply the disturbance at 0.1 second. Then this is the loop for the Euler integration method. So the first one, you can write del delta I plus 1 was del delta I plus TS omega base into del omega, and that's it. That is the disturbance. So we keep it as it is. Then we have del omega was del omega I plus Ts over twice H. This should be del PM plus disturbance 1 should be there. And then we have to change here. That is K1 del delta minus D minus D del omega. There shouldn't be any 1 due to the linearization process. Then we have minus K2 del EQ prime I. Hope it is done. Then we have the third one is del EQ prime I plus 1. Then del EQ prime TS over TDO prime. This is del EFD. This should be minus K3 del EQ prime. And this one is already linearized, minus K4 del delta I. And of course, we don't need any of these because those were the algebraic variables there. But in the linearized model, we don't have any algebraic variables left within the model. So we can get rid of those. So simply we have to type these 3 state equations along with any disturbance that we are going to apply. So let's name it as linear SMIB third. Okay, so get rid of this. Anything left? Probably not. Get rid of the equations. And then, okay, now what's left? We can clearly see that, well, there are some warnings for us. And as we did for the nonlinear model, if you remember, we had to define the initial conditions for that. Okay, so here our states are now not exactly delta dot or delta. It has been transformed into del delta. Okay, in the nonlinear model, it was delta. Now it has become del delta. Then it was omega. Now it has become del omega, and so on. It was EQ dash. Now it has become del EQ dash. We have the calculated values for this. We have delta 0, omega 0, that means the initial condition, talking about the initial condition, and EQ dash 0. But what would be this? Del delta naught, del omega naught, and del EQ dash naught. Any idea how to get these values to start with? Because we have to start from some initial operating point. So if you remember, when we started the topic of linearization, we told that, well, delta can be represented as this, right? So from this equation, we can also write del delta. We can get the expression of del delta equals delta minus delta naught, where delta naught here means it is the value of delta at the initial of equilibrium point or the initial operating point, right? So if I'm looking for this del delta value at the first instance or at the initial operating point, we can call it del delta naught. And what would be the value of delta then? Delta should also take the value of the initial operating point. Okay. Remember, delta is an arbitrary variable that depends on the initial operating point, value of delta at the initial operating point, delta naught, plus any deviation. So at the initial operating point, this delta value and this delta naught are exactly same. Why? Because we are considering that it is an equilibrium point or it is an steady state operating point. So because it is a steady state operating point, at the very beginning of the simulation, there would not be any deviation. All the deviation variables will start from 0. And that's why this vector over here, this vector of initial values, we can simply call them as 0. Okay? Is it okay? Any question? No question. Okay. So with that information, we can now simply write the initial conditions which are required for our simulation. And that is del delta. And that is actually true for any linearized model. That is true for any linearized model, for any dynamic system. Whenever you linearize, then you simply can take the deviation variables, initial values of the deviation. Remember, we also call it as the deviation variables. The delta variables here are deviation variables. So to start with, we are saying that, well, our system is at some equilibrium point, at some steady state equilibrium point. So there should not be any deviation. Okay, there should not be any deviation, no deviation. And that's why there is another way to explain this, that all these deviation variables to start with will have or will take a value of 0. So del delta is 0, del omega is also 0, and del EQ prime is also 0. So now let's check the condition or the situation without any disturbance. Remember, we did the simulation. We did the simulation in the nonlinear case. We started with no disturbance case. Okay. So, okay, let's check. We also have to define delta PM. Actually, delta PM is actually given in terms of disturbance. So we can, and also delta EFD. These values are not given. We can say, well, delta EFD is 0, and del PM is actually our disturbance. Okay, del PM is actually our disturbance. So we can keep del PM 0 and we can add some disturbance, all the same. We can make it 0 and we can make this non-zero, or simply we can get rid of delta PM and we can simply keep this disturbance 1. Okay, but we have to know that this disturbance is actually some sort of delta PM, because in the nonlinear model we applied some PM, change in PM, and we want to compare the response here for the linear model with the one that we got for the nonlinear model. Okay, so we have given them the values of zeros. Now we plot it. So the plot should be now T and del delta, del omega, because these are the states now. So for that, let's open one. Let's want to show it. Let's open the synchronize part. Okay, just a minute. Make it ready, because we have to bring the simulations for your observation. Okay, now let's run it. Okay, so that is done. And then we copy the figure, and take it to some okay, so let's make it visible to you now. Okay, so do you see the PPT slide? This is the response. Is it visible?
Yes, sir.
Okay, so this is the response actually for the linear model. You see that without any disturbance, actually we have the profile, the trajectory are all along the 0 line. That is their initial condition. If I want to compare it with the nonlinear model, okay, so if I bring the nonlinear response that is actually recorded here, so you can see without the disturbance, this was the response for the nonlinear model, for the same system, nonlinear model at the same operating point. So because it was the nonlinear model, so the initial condition was non-zero, okay? So initial condition delta naught was some non-zero value. Omega was at 1. EQ prime was some 1 point something, probably 1.2 something. So, but the main thing is that they stayed at their initial value, okay, throughout the simulation period. That means your initialization is fine, okay, your initial simulation is okay. Now, our target is to compare these responses, okay. These were the responses for varying degrees of D. Remember, we changed the D parameter and we got different responses. This was the initial D value, for the initial D value. This was for some very increased value of D, and this was probably some negative value of D. I intentionally put there just to show the scenario whenever there will be instability, what would be the responses like. So now let's try to compare. So the first comparison is done. So let's make new slide, make some space for the new results. Okay, so let's go back to MATLAB. And what we would like is this B parameter was set at 0.5 initially, we can see. But if I check back the nonlinear file, we actually had 3 values, okay? Okay, so in line number 7, there is one additional comment that for stable response or more stable response, we can set D to 5.0, and for some unstable response, we can set D to some negative value. So the first one that we'll try to compare is D equals to 0.5, for which actually we have got our eigenvalue calculated, where we have very low damping, okay? So let's see. So what we have to do, there are many files. So we have to go to the linear SMIB third, this file. And now we have to apply the same disturbance because we want to compare the responses 0.2, and let's start the simulation. Okay, we have got the response. So let's copy it, copy the figure, let's paste it, and let's bring it to you. Okay, so let's bring it to you. So this is for the linearized model. Okay, this is for the linearized model. So the simulation actually started from 0. If I bring this one now, this is very big compared to that, but even then we have to bring it. So you have to then resize it, make them look identical, smaller. Okay, almost there. Yeah. So now, can you compare? So the values here probably are very small to see, but of course, they are oscillating around some other values because that is non-linear model. Their initial condition is different. Here for the linear model, the initial condition is different, but the pattern, you can say, well, it's almost identical, okay? But to have more, I mean, what should I say? To have a more better comparison, what you can do, you can superimpose these two, okay? That means you can superimpose the first one here, that is for the delta, and the first one there. You can superimpose the second one on the left, the omega, and the third one on the right, on the third one on the left, okay? But on the naked eye, I think, except the delta is a little different, but the oscillation frequency probably looks almost identical, okay? There would be a little difference, remember, because this linear model is actually some approximation of the original nonlinear model, okay? This linear model over here is actually nothing but some approximated model of the original nonlinear model. But the pattern is almost, I mean, you can be satisfied with that. And we can say that, well, the linearization is more or less fine enough to analyze, okay, the system further. By analyzing the system further means if I want to improve the damping, then I can choose the linear model. Okay, I can forget about the nonlinear model for the time being. I can hide it behind, I can bring it in front, and I can apply the well-known linear control techniques. I can check its controllability, I can check its observability. I can try to design, let's say, very classical PID controller by using some classical tuning technique like Ziegler-Nicholas tuning technique or internal mood control technique, etc., etc. These are the classical techniques. And of course, I can go for, I mean, much more complex or modern control techniques, even like robust control technique or model predictive control technique, or maybe adaptive control technique, and so on. So what we can do, we can take this linear model over here, the response of the linear model, it is almost identical to this one, except there is some rise at the initial part here. But other than that, they are almost identical. Okay, so so what we can say, and another thing, probably you can scale them, okay, on the same scale. Probably scaling is another factor because the scaling is different. You see, it is the oscillating from 0 to 0.33, where this oscillation you can, if I magnify, probably you could see, but you can do it on your own. You can check the oscillation and you can scale the figure files. You can the same scaling, and then the comparison would be much nicer. So so that means you can apply linear control technique to design some control for the linearized model over here, and then you can come back and take the control block and try to control the original nonlinear model. Remember, our model itself is nonlinear, okay? But we are going into the linear domain just to help us help us in designing some or applying some linear control techniques for designing some control for the system. Once we design the control there, then we hope that the same control for this nonlinear system would be sufficient at least around a certain equilibrium point. Are you getting the idea? We would design a control here. We are not going to design nonlinear control for this original nonlinear model. That's a little difficult. We need to adopt some nonlinear control techniques. We don't have the knowledge, probably. I don't know whether you have taken nonlinear control course or not. But if you have, then you can, well, you can apply the nonlinear control technique directly here. But an easier way is to, of course, do some mathematical manipulation, get the linearized version of the nonlinear model from this one to this one, check the responses. Well, the responses are almost identical, then you should be satisfied. Design some linear control, for this system. And let's say it's a PID. So what you will get, ultimately, you will get some KP, KI, and KD, nothing else. Some KP, KI, and KD values would be obtained. Whatever control technique you adopt, some KP, KI, KD would be obtained if you apply PID control technique. Then you take that PID controller and implement it for this nonlinear model of SMIB system with the hope that the system would remain stable, of course, around the vicinity, of course, in the vicinity of your original nonlinear, whatever equilibrium point you are talking about, delta naught, omega naught, and EQ prime naught. So your control would be sufficient to control the nonlinear model. Your controller should be sufficient to control the nonlinear model around this equilibrium, okay? Not for the whole nonlinear model, because the controller is not designed for the whole nonlinear model. It is designed for a certain equilibrium point and for around that equilibrium point, okay, in the vicinity of that equilibrium point. So this nonlinear control is not a global controller for this nonlinear block. Okay, it's not a global controller. It's not a globally stabilizable controller. You can say it is a local stabilizable controller. So any disturbance applied around this equilibrium point can or could or should be sufficient for stabilizing the system. Okay, but not for all equilibrium points. This KP, KI, and KD may not be good enough to control this nonlinear system for any other equilibrium point. Okay, it may or it may not be. depending on the degree of nonlinearity. Okay, so we will also look into that actually. Okay, we'll design probably some controller, and then we will try to come back and implement the same controller for the nonlinear system and try to see the responses, whether it is good enough or not. Okay, we'll do it inshallah later on. So that is in the control design part. Okay, so this is the response, and let's see, everything else. Now, the next thing is that, can you do it in Simulink? Yes or no? Okay, let's check first. Before that, let's check the variation in response, change in response due to some change in D. Okay, the second value was 5. Okay, so you can clearly see, okay, for 0.5, we can clearly see that, well, this response, you see there is oscillation, and even after 30 seconds, the oscillations are not completely dying. Okay, it has not settled to any equilibrium. It is still oscillating. So this is because of the low damping ratio. Okay, the low value of zeta associated with these two states. Okay, so we can see now that, well, without the participation factor calculation, another idea that you can get that from the diagram, from the time domain simulation, we can also get the idea that which states are lowly damped. Okay, so this is the lowly damped state. These two are the lowly damped states. Okay, that is 0.0009. The third one is the EQ dash. So the third eigenvalue was probably associated with the EQ dash state. But another way to achieve this information is with the help of the participation factor calculation. So to enhance the damping or the damping ratio value, what we can do, we can go to MATLAB. We can change the D value in line number 7, and we can increase it to 5, just to make a fair comparison between the nonlinear response and the linear response. So let's simulate that again. Okay, it's done. So let's take the result. Let's take it, let's copy it, and paste it somewhere in the PPT file. So, okay, that's good enough. Now we check the, okay. So do you see the PPT file? Hopefully. So let's make it small enough so that we can accommodate this one side by side, of course. Small, okay. So now you see, do they look similar or identical? The responses, the left one is non-linear one that we did earlier, and the right one is the linear one that we are doing today for damping D equals to 5. So again, to have far more better comparison, you can again superimpose these two. Okay, delta with delta, omega with omega, and EQ dash with EQ dash. So with D equals to 5, probably they look almost same. Okay, almost same. So again, that proves that, well, if we can change somehow the value of D damping, if we can incorporate some damping into our system, then of course we can expect that the damping ratio to be enhanced. So let's now, to finish this lecture, let's now go back and check the eigenvalues with this new value of D equals to 5. Okay, and calculate the remaining few things like the damping ratio, the frequency of oscillation, etc. So we have to go to MATLAB, close it. Okay, so let's go to the eigenvalue file. This was eigen SMIB third, and simply we have to do what? We have to simply change this to 5. And then again, what we do, we simply, yeah, these are uncommented. Okay. So what we have done, let's see. Yeah. So what was the DD earlier? Can you recall? Let's do it again. 0.5. Just try to track the DD value, the eigenvalues, the real part. You see it is 0.0438. Okay. Very near to the y-axis, 0.0438, although minus, but 0.0438. With d equals to 5, simply it jumps, it improves, and it goes to 0.3251. Okay. So it's now far away from our y-axis. That means it is more stable. It is moving towards more stable zone. And interestingly, the third one actually has become now the dominant eigenvalue. So by simply changing the d, although here it is a very simple technique, okay, here I'm simply playing with d, but in real world, actually, you have to incorporate some control technique or some control effort, or you have to attach some device to your SMIB system just to do this job for you. Okay, it's not so straightforward. Okay, to simply change the d and simulate and see the response. It has to be done. It has to be taken from some physical means, with the help of some physical means, practical means. What about zeta? It was 0.009. Now it has increased to 0.0069. Okay, so you see the enhancement. It has now increased a little bit. Okay, so it was 0.0009. It has now become 0.0069. So you can analyze your stability with the help of eigenvalues. You can check your eigenvalue locations. You can identify which one is your dominant eigenvalue. You can check the damping ratio, and you can simulate it in linear mode. That means x dot equals ax plus bu. You can have the time domain simulation, and you can compare it with your original nonlinear system. Okay. So with that, probably we would like to conclude today with the question that, well, now can we simulate this linear model at least in using Simulink? Can you do that? Probably you can. So that would be probably your second assignment. But before we leave, let me ask you the progress about the first assignment. Remember, your deadline is probably after mid, or when you have exam, on the day of the exam, probably you will get up to that day as your submission deadline. So once the schedule for your mid exam will be finalized, then accordingly I will finalize the deadline of submission for assignment number 1, which was given earlier, but now I'm in a position to give you assignment number 2. Okay, what about the progress of assignment number 1? I have got questions from 2 of you, Ashif and probably Naushad, if I'm not wrong. Right? And probably similar kind of question, similar kind of query about the formation of L matrix, LSS, the self-inductance matrix for the synchronous machine. So what I suggested, probably most of you have seen in the messenger group, I suggest that you continue with your derivation and you submit your assignment. If you feel there is mistake, no problem, there could be mistake, but you have to show it that the mistake is there and this is why there is the mistake. Okay, I did it pretty long ago, and I don't know whether the file is left now. I just copied it from there. Probably it could be also some typo mistake. Okay, could be also some typo, but I don't want to change without any proof. Okay, so I want the proof from your side, and then I will change, no problem. There could be mistakes. Any question?
Sir, in second question of the assignment,
Yes.
the omega matrix, there is this identity matrix of the omega matrix. Is it correct also?
Let me share. Okay, I don't know what you're talking about. Where is the assignment? Let me see. Assignment 1. Assignment 1. let me share, then probably he could answer your question. Yeah, this is question number 1. This is assignment 1, question number 2. Yes. What is the question? Omega.
Sir, yes, sir,
Omega here is simply d theta over dt. That means d, you see the theta s here, okay?
yes,
So wherever you will get d theta s over dt, because remember you have to do some differentiation with respect to time. So of course there will be some term arriving in the form of d theta s over dt. So wherever you will get d theta s over dt, you simply write them as omega. That's it.
then in front of this matrix, I think there is something 1/3 or something is coming like. And
Okay,
also
again that depends which k, I mean which k1 and k2 you are actually taking.
So K1 is 2/3 and K2 is I think K1 is 2/3, right?
It's up to you. You choose either without the square root or you choose the set with the square root.
Oh, okay, okay. So we can choose also √3/2 as
Yeah,
K.
you can check, no problem, because I haven't given any choice here. I have simply written k1 and k2. Okay.
Okay, okay.
So probably for some combination of k1 and k2, one of the combinations, probably there will be nothing, but for some other combinations, probably there will be something. It doesn't matter.
Okay, but there's a number of zeros in.
Zeros
Right.
will be unchanged. Zeros will be the same.
Okay, okay.
There will be only 2 entries. With lambda 0, actually all of them will be 0. There will be only entries for these 2. Okay, and probably some constant factors will be there, but that would be again based on the choice of your k1 and k2.
Okay.
Okay, thank you. Any other question? Okay, if no other question, then okay, let's conclude it here, and inshallah we meet on the next class next Tuesday. Assalamu alaikum.